I should wait and give my apologies at the end, but just here's a preview. I apologise for anybody I offend today, because I probably will, but I figure out if I offend all of you, then it's fair, right? Does that kind of cover all bases? Okay, here goes. We're going to look at section 8.3, and we've got two things in 8.3. Oh, not 8.3, tell me. 8.5. That shows you how bad I am. First, did we do last time hypothesis testing for proportions and for means? And we probably finished that. Would you agree? Because great. So we're doing 8.5. There are two things in 8.5 then. We're still on hypothesis test. Only now it's going to be the difference between two proportions and the difference between two means. So it's really just an extension of what we already have done. So I guess in a way that is a little bit better. It's not really so much, it's not mostly brand new, it's mostly regurgitated, but it's just taking into account another, whoops, there we go, taking into account another situation. Right. So when we did hypothesis testing last time, the general story went something like that. Let's do proportions. In the past, 22% of people used to be vegetarians. Someone thinks that's changed now and there's more vegetarians. And so he does a little survey, and 42 out of 100 people say they're vegetarian. And then you go off and you see, is that statistically significant, right? That's kind of where we got. That's a basic story. So how are we going to change that? Well, we are going to have a story where there's two distinct groups, and we are going to look at, is there statistical evidence that we can use to compare the two? And the comparisons are, is one bigger than the other? Is the first one less than the other? Or are they different in some way? So let's put a story to it. Suppose we went and did Scottish people as our first group. And over here, we're going to do Americans as our second group. And we are interested in what percentage of these people have been to a foreign country on holiday last year, right? So in 2019, right? Did you go to a foreign country at least once on holiday? And the reason they're asking that question is that they believe that Scottish people go on holiday to a foreign country much more than Americans do. So the Scottish group consisted of 200 Scottish adults, and the number of those who'd been to a foreign country was 180. And the second group was 350. And since I'm making this up, I can make this number anything I like. Was 278 out of 350. Which is probably much larger than it is in real life, but I just wanted some data. And our question is there enough evidence to prove the Scottish people went on holiday more than Americans? Oh, this guy here is 90%. So 90% of Scottish people went on holiday. Probably unrealistic, we'll pretend it's true. And on the American, side, it came out about 79%. Now, if you look at this superficially, doesn't it look like 90% is definitely bigger than 78%? So it's highly likely that that statement is true, but you're not allowed to just look at that raw data and say, yep, I've proved it, move on, none to see here. Because the hypothesis testing process says that you have to go through a very rigorous procedure. I'm going to show you how to do this fella by hand once, and then we'll show you how you do it in the calculator, because it takes a lot of time if you have to do it. Right. So, step one is going to be set up the hypothesis. Right. Now, this time, the null hypothesis consists of P1, the population parameter for Scotland, is equal to P2, the population parameter for America. So these would represent the real number. You notice this is just a sample of Scottish people. This doesn't guarantee that the population is 90%. Couldn't that just be a high sample? You know, if I did another sample like 200 Scottish, maybe only 80% had been to a foreign country, right? If I did a third one, it'd be 72%, all that kind of stuff. So this says the population of Scottish people, the percentage of Scottish people is the same as percentage of American who went on holiday. Now, in my story, is there enough evidence to prove that Scottish people, who's number one, is a bigger percentage than American people, number two? Are we comfortable with how you create from this story that particular thing? Right. Now, there are three versions of this, just like last time. This is a right-tailed test. How do I know this is a right-tailed test?
Because of the direction of the lesser than sign, greater than sign?
If one's greater than the other, you're going that way, which is to the right. If it had said, if a different story we wanted to prove that was true, aren't we going to the left? So that'd be a left tail test. And you know, sometimes you just want to prove that it's different. You're not quite sure if it's bigger or smaller, but you're pretty confident it's different. And when it's that kind, don't we call it a two-tailed? Okay. They sometimes ask you that, don't they, in the homework? Is it left-tailed? Is it right-tailed or something? So that's how you would decide. Well, that's step one. Is it not pretty much identical to Monday? Same kind of thing happened. Step one. Step two. Let's get our statistics. In particular, let's get the Z-score. And the Z-score is P1 hat take away P2 hat over the standard error. And that's me just telling you, that's what the formula is, right? The difference between the proportions divided by the standard error. The standard error is a name that we use to represent the standard deviation of the sampling distribution. And that's a mouthful, so we'll call it standard error again. It's given by this formula. Darn it. It is given by this formula. I need it over here. It's such a big formula, I need room. Square root P bar, 1 minus P bar, 1 over N1 plus 1 over 10 N2. Do you see why you probably are, you're going to use a calculator to do these questions rather than try to do this by hand? Now, this thing is not P hat, it's called P bar. That's how you say it out loud. P bar is made up from this data here. So how do you get it? You add the number of people in Scotland who've been to Europe. You add the number of people in America who've been to Europe. You divide it by the number of people in the Scottish sample plus the number of people in the English sample, the American sample, sorry. That adds up to let's see, 278 plus 180. So that's 458 out of 550. That's going to be 458 divided by 550. And the answer that I'm coming up with is 0.833. So to get the standard error, it's the square root of 0.833. That's p bar. Multiplied by 1 takeaway p bar. That's 0.167 times 1 over that number, the Scottish sample, plus 1 over the American sample. I think I probably already sold you on the idea that you want to do this with a calculator, but I think it's worthwhile to show you once in your life what you had to do by hand so that you'll appreciate that the calculator is just going to do all this automatically. And we aren't even finished yet. This is just getting sort of a kind of there. So, you remember our Z guy? Our Z score? That's what we were trying to get. It's P1 hat, 0.9. Take away P2 hat, 0.79. Divided by, oh, I forgot to get this guy. Let's do it then. Square root of 0.833 times 0.167 times, put a bracket around it, 1 divided by 200 plus 1 divided by 350, close the brackets, maybe 2 brackets to be sure, and let's do that again. Square root 0.833 times 0.167 times a bracket 1 divided by 200 plus 1 divided by 350. Much better. I didn't like the first answer. I knew it was wrong. 0.033. All right, now I can return to this fella. P1 hat, take away P2 hat, divided by standard error. The Z score is nothing 0.9, take away nothing 0.79, divided by 0.033. And the answer I'm going to get here is 3 point lots of threes. Okay, let's pause again. To get the standard error, this is the weird formula. To be able to use the weird formula, don't have to find this thing called p hat, p bar. P bar is made up of how many said yes in Scotland, how many said yes in America, divided by how many people in the Scottish sample plus how many people in the American sample. That's p hat, p bar I should say, that's p bar. That's that guy. Now that you know that guy, you plug it in here, 1 minus it here, these two guys, you got this guy. After you did all that hard work, you calculate the Z score, and you're finished with step 2. Third step, get p-value. Can you remember yesterday, isn't the p-value the probability that your Z score is bigger than this number, or the probability your Z score is less than this number? Just by looking at this number, can you tell me if it's going to be Z greater than 3.33 or Z less than 3.33? How will I get the p-value? Z greater than 3.33 or Z less than 3.33? That's really your two choices.
Greater than?
Greater than. Now, if you have issues, Will you look over here? See that greater than? This is always the same thing. Right, greater than here, greater than here. Second way of telling. If it's positive numbers, it's always greater than. If it's negative numbers, it's always going to be less than, right? It's kind of guaranteed. Now, this fella does require a calculator. Does anybody remember where this guy's living? How would I be able to get this answer?
Is that one in test?
I wish it was, because almost everything else is, but no, it's not. It's probably one of the few things it's not that we've been doing in the last week. It's second distribution, and it's number 2. And we are going to find the probability using the normal CDF that we get a Z score bigger than 3.33. So bigger than 3.33 is 3.33, comma, my magic 999, comma, 0, comma, 1, finish brackets. Olivia, can you hear me?
Yes.
What if you, now this isn't a joke, I just want it out of my brain so I won't get distracted. What do you phone if you need to phone the police or ambulance
Here?
in Australia?
Oh, in Australia it's 000.
000
Yeah. And what is it in Scotland?
999.
Yeah.
In America, it's 9. Do you know that if you are going to a foreign country, this has just hit me. If I'm going to a foreign country, do you know the first thing I should probably look up? How do you phone the police?
Well, here's something for you. So last time I was out there, my uncle and I wondered the same thing. So my uncle called 911 and he actually got through to 000. Because I guess they have so many Americans who come out and call 911 who need the police, they automatically redirect it to 000.
See, the next time you go, will you try 999 just in case there's enough British people?
I imagine there would be. I'll give it a shot.
I'm too scaredy cat, and I've not told you to do this, but if you just casually, accidentally type 999, do you get through to 911? Don't
That's
do
a
it.
good question. I might ask
Don't do
somebody
it.
else to do that.
I'm not going to, don't you do it. I'm just curious. Okay. Back to this guy. The number that we got here was a weird 3.43 e to the negative 4. Wish this line wasn't here. Isn't that 4.34 times 10 to the negative 4? I think this one is doable. You agree? It's still, you know, writable, right? Normally, I don't bother writing this thing. See, if this is e to the negative 11, I wouldn't bother writing all those zeros, right? Everybody will just say, Garner, that number's 0, almost, right? It's virtually 0. Okay, step 3, find the p-value. We just did it. Conclusion time. Is the p-value less than alpha? And I've darn well forgot. You see my story up here? You have to be told alpha. Let's suppose it was 1%. Is 0.000434. Is it less than 1%? And the answer is yes. Resounding definitely yes. Okay, what's the sentence that you kind of would sentence that I write now that I've got this yes? It's a kind of special sentence. This is statistically significant. In particular, we can reject H naught, and so HA is true. And back to our story then. We have now proven in a kind of lawyer-esque way that we can say with our heart on our hands and be really comfortable about it that Scottish people go on holiday to Europe more often than Americans would. to a foreign country. Why can't we just make life easy and use these two numbers? Well, if these sample sizes were really small, suppose this was 20 Scottish people and 35 Americans, right? Just pretend you did a tiny sample. Couldn't you quite easily get these numbers just by pure chance? And it's not because Scottish people go, on holiday more than Americans, right? Isn't part of the information the size of your samples? And you've got to have a way of giving more credence to big samples and giving less credence to very small samples. And one of the ways that that is done is through this very long, messy numerical process. So you can imagine if you had to do every question by hand, how long it's probably going to take you, right? It's going to have the same things, you're just going to put different numbers in, right? It's going to be the same mechanics, but really messy. So I'm now going to show you the same calculation, same data, and if things work out correct, shouldn't we get a p-value 0.0004, right, roughly? Now, the answer that the calculator is going to give might be a tiny bit different, but you've got to remember, I rounded off to 2 and 3 decimal places here. Can you imagine the calculator is probably going to do it too? I think calculators work to 12 decimal places and they show 8. Right, so there's going to be a little rounding off, not in a biggie, just means it's more accurate. Now, the big question, where is this fella hiding? The whole hypothesis test deal. I mean, come the final, we could stare at our calculator, but hopefully eventually we'd start hitting buttons to find its menu. Where is it hiding? I hear stats. Well, I see your lips move. And would you agree that there's a little menu at the end that seems to be where everybody hides, except normal CDF? Isn't that the only guy that doesn't hide in this menu, right? It's very much in here. Now, there's tons of choices, most of which have been used, not all of them. This is 2 samples, proportions. So who are we using? It's in the screen. What number?
6.
Yeah. Does it make sense that 2 proportion z-test? I guess the only other one would be called a 2 proportion t-test, but that doesn't exist, so you don't need to worry about it. When you do proportions, the math tells us that it's always a z-score. Proportions just work differently than means. X-bars and things works different. Right, in this case here, I'm going to hit it. And now we just basically have to fill in these things. X1 is the number of Scottish people, so that was 180. N1 was out of 200. X2 was the amount of Americans that had been on holiday. N2 was how many we asked. Can you see you've got that little which one to choose? So I want P1 to be bigger than P2. So it's a little bit cryptic, but basically P1 bigger than P2. Do you see it's that last one? P1 bigger than P2. And then I can do calculate. And boom. The Z score is 3.1 and change. What did I get? Well, Z score is what, 3.2? Let's give myself a little break. I got 3.3. Do you know the reason I got 3.3 is because I rounded off to 2 decimal places, and I bet you if I rounded off to 6, it would be that number. What does the p-value look like here? Well, let's see if we've got it. 6.9 e to the negative 4. That's pretty close to mine. Didn't I get, I've lost the darn thing now. Didn't I get an e to the negative 4 something? I can't remember what it was now. It was at least it was something in that range, wasn't it? Don't worry about the discrepancies. I mean, if you want to get the same numbers by hand, you're going to have to write everything to about 8 or 9 decimal places, right? I don't really feel like doing that. Isn't the conclusion going to be the same? Statistically significant, and we are done. So So let's make life easy now and just do stories using the calculator. Right. Okay, so got a story. What story am I gonna do? Let's do a clinical trial, pretend one. There's a new cancer treatment out, and they want to see whether or not this new treatment is doing a better job than whatever the old treatment is. So they do that, clinical trial thing. Let's make it simple. The new treatment is just a wonder drug, right? You take this pill and it reduces the size of the tumor, right? There's some drugs that do that, right? And let's say the old treatment was the same, right? You take a pill that reduces the tumor, off we go. Now, when they do success in clinical trials, things like cancer, I mean, sometimes the success is that the cancer can't be found, right? It's gone. But a lot of the time, sometimes success is based on a thing like how many of my patients are still alive in 5 years. Because, some treatments don't actually so much destroy the cancer, but don't some treatments prolong your life? And they give you, they give you a few extra years or 5 or 10 extra years. And that's pretty good, right? That's not a bad thing to do. So in this story then, the old drug, I'm calling that number 1. And then the new drug, I'm going to call that number 2. And in the old drug, they did a clinical trial, and they had 500 people in this clinical trial. And the success of that drug was 362 people out of 500 were still alive in 5 years. Right? So it's pretty good treatment, right? Pretty good success rate. The new drug, they had 1,000 people taking the new drug. And the success on this 1,000 was 740 people. And I'll turn that into a decimal just to see what's going on. Just for my benefit. Superficially, doesn't it look like the second drug has a better success rate than the first? Now, if that was true, if everybody took the treatment, it's what, an extra 1.5%? Might not look particularly big success. But doesn't that mean one more person out of 100 might live? And yeah, I think it's worth it. One more person that might have died can now live. It's worth it, especially if you're that person, right? Very important if it's you, if you're that person. So let's get this thing set up. Null hypothesis, alternate. The null hypothesis is always going to be that the two percentages are the same. The alternate depends on the story. At a significance level of 1%, is there enough evidence to prove the new drug is better than the old? Now, in this case, isn't that proof that the new drug is better than the old? Because what you're really saying is the old drug's worse than the new, but in the English language, I'm taller than you, you're shorter than me, is saying the same thing, right? We go. Number 1 done. Right, should be ready. Data's going in. Start. Tests, number 6. I'm just putting this here if you watch the video. I've forgotten what this is called. I mean, I know what it is, but what it's called in the calculator. Is it 2 proportion Z-test or a name, something like that? Okay, 2 prop Z-test. Okay, let's see what we get here. Group 1 had 362 successes out of 500. Group 2 had 740 out of 1,000. We're looking for P1 less than P2, so that's going to be the middle choice. And then we're going to hit calculate. And in the homework, they ask you very often for things like, what's the test statistic? And guaranteed after that, they're going to ask you, what's the p-value, right? When they ask you for the Z, the test statistic, they're talking about the Z-score. And can you see in this case, it's negative 0.661. And the p-value is 0.25. Can you see that's where you're going to suck out all your data? Now, they might or might not ask you for P1 hat and B2 hat. If they do, you use these numbers, right? And so on. But that number there is actually the most important number of everything, right? The p-value tells you the story. So let's go straight into it. So that would be step 2. There would be step 3. See how quick it is in the calculator? You get the numbers right away. And let's do the conclusion part. Is our p-value less than alpha? Is 0.25 less than 0.01? Do we say yes or no? No. That's bad news, isn't it, as far as, you know, the pharmaceutical company. This is not statistically significant. So we would not reject H naught, and so H is true, right? We just wouldn't reject H naught. That doesn't mean in English that just because it's not statistically significant, it doesn't mean that this drug isn't better than that. It doesn't mean this drug is worse than that. It also doesn't even mean that they're equal. It simply just means we haven't any evidence to make any conclusions at all. Could be bigger, could be worse, could be the same. We can't tell. It's pretty much a non-event story, right? We know nothing. It's like we never even done the test, right? We know nothing. Because sometimes they give you a little list of things. What does this mean? And one of them might say, oh, this means that both drugs are equally effective, right? Based on that, that doesn't mean that. I mean, if my gut feeling is, if anything, isn't it leaning slightly in favor of the new drug, but not enough that the statistics found it? Couldn't that just be randomness as well? You know, if I did another sample, couldn't I end up with 75% here and 73% there, right? Could happen. Not enough evidence, it's finished. And some stories are going to do that. That would be bad news for the pharmaceutical company. Can you imagine that they may have spent, you know, months or years developing this new cancer drug? They put it to clinical trial, compare it against the, you know, the generic drugs that's being used today, and this horrible number appears. What do you think the pharmaceutical company does once this has happened?
They start throwing out outliers to try to skew the data.
The government would sue their aspidestras. That would not be legal, and they would definitely be in trouble. If they ever get caught doing that, the fines would bankrupt them. In fact, some people would end up in jail. I know the temptation. Unfortunately, probably what would happen, well, there are two things that can happen. The most likely thing is they just say, to heck with it, it didn't work. We've 12 other drugs that we need to worry about. You know, one of them's going to make it. I've read somewhere that only about 1 in 10 of all pharmaceutical drugs that are being in development, only about 1 in 10 of them end up being effective and go on the market. So if you can imagine, every one of these might cost $1 million or a couple of $1 million, you know, research, development, you know, doing the whole thing all the way to the end, right? If only 1 in 10 make it, can you imagine that pharmaceutical companies have a big expense? And so I've mentioned that to my other class. That's the main reason why brand new pharmaceuticals cost so much. It's not that they cost, you know, $500, you know, a bottle to make the pills. Aren't they trying to recoup all the losses from the 9 drugs that they spent millions on that didn't go anywhere? Yeah, and I begrudge the heck out of it as well, because when a new drug comes online, isn't it typically very expensive compared to the generic? And so if you've got money, then you're going to probably get better medical treatment because you're going to buy the dear drug. I think America's system is weird. Well, not weird, it's just different. If I went and got a new drug and I went and said to my doctor, I heard about this new drug, I want to get it. If I went to my insurance company, they won't allow me to get it directly, but they might put it in a list where if I get a generic, they'll pay 90% of the drug cost. But if I get a non-generic, won't they, you'll have to pay 50-50 or something, right? They do that kind of thing. I think that is, I don't know enough because I always get generic, but I think that's how it works. Yeah. Do you know how it works in Britain? Because it's National Health Service. You don't get the new drug. National Health Service is not going to fork out money. They'll wait until it hits generic and then you'll get it. So you won't have a choice. Well, no, I'll wind up back. You will have a choice. If you go private and you pay for all your medical, you can get anything you like. You just pay for it. But if you use the normal system, you won't get that drug. Never would. They'll make a simple calculation. 1 new pill, 100 old pills. We can treat 100 people for the price of 1. Just ain't going to happen. So, got that little bugaboo out of my brain. Oh, I got to tell you, it's in my head. My mum's passed away now, but my mum had on her cheek here a growth that looked decidedly something wrong with it. And I was back home on holiday and I wasn't happy about it. And so I finally got my mum to go to the doctor. And the doctor had a look at it, and the doctor didn't like the look of it either. And the doctor says, okay, we'll put you in, you got to get, someone's going to have a check and that, do a biopsy on it, whatever. And so I thought, great, we're working. Proviso here, if you're really old in Scotland and things are short supply, then don't expect good treatment. If you're going to have cancer, be 18, don't be A. The waiting lists are different. So anyway, back to the story, my mum with this growth. So I waited and I was there, and within a week, which I was amazed at, I was really happy. Obviously the doctor had been really concerned and maybe put a rush job on it. I got a letter saying turn up tomorrow and they're going to take, a look at my mum's growth. And I thought, hey, that's good. This is pretty fast. I know what Britain's system was like. And I go there and I take my mum. And do you know what they did? They took a photograph of it and they sent the photograph to a specialist who looked at the photograph and said, yeah, that looks like cancer. Well, though it took us a week to get the answer. True story. That was my mum's diagnosis. They just, I guess this guy, I'll make him, he's in Surrey, wherever he lived, right? They just sent him an email with a picture, and I guess he looked at the picture and he knew enough about what were cancerous. And so my mum got, well, I was back home by then, but my mum eventually got the treatment. She came and they cut the growth out, and, that was the end of that. But what would you have done if that was the American system and your mum was going to hospital and they said, yeah, we'll take a picture of it and see if somebody in Kansas is going to decide on it? She was lucky she got treated, to be honest, so I guess I shouldn't be that bad on it. But it was an easy operation, right? They just froze it and cut it out and stuck a plaster on it and she was good. But I don't think it would have been such a cool idea. So I'm just wondering if maybe one day I'll go to a doctor in Scotland and they'll say, could you just tell me your symptoms over the phone? I'll see if it's cancer. Could happen. Okay, I think I'll do one more of these percentage guys, right? These proportion ones, just to give you a feel for how it works. And then we'll move on to the other one, which is difference in means. So I need to make up another story. Okay. Oh, let's do vegetarians. Is anybody here a vegetarian? Because I'm about to insult you. You are? Okay, I can't pick on vegetarians then. I better not. Okay. We'll have two groups, country A and country B, who may or may not be vegetarians. And country B may or may not be meat eaters. Okay? And in country A, they went and asked people, and there was 200 of them, and they went and asked them, are you happy? And 120 of them said, yeah, I'm pretty happy. And they went to country B, and there was 300 of them, and they asked them the same question, are you happy? And 195 of them said, yes, I am happy. And this social scientist wanted to see, and I'll phrase it this way, is there enough evidence to show that these two countries are different? Now you might say, well, the data looks like B is happier than A, but let's just have this as a difference, right? Because I've done a bigger than, I've done a less. We need to say I'm not equal to, right? So that's why I've done that. So let's find out what it would look like. Stage one, set up the hypothesis test. Well, the first population is the second, right? Percentage of people in the first is just as happy as the second. And this one, not equal to. Left-tailed, right-tailed, two-tailed.
Two-tailed?
Did you say two?
Yeah.
I hear, I agree. I better have an alpha for this, don't I? Let's have a 10%. Right, that's part of the story. Right, stage two is going to be Z-score. And stage three is going to be p-value. And aren't both of those going to come out of the calculator? So here goes. Stats, tests, to proportion, boom. Okay, back to the data, 120 out of 200, 195 out of 300, and a not equals to. Do you see the not equals? The first choice? Isn't this the guy that decides which one of these three that we use, right? So whatever HA is saying, that's how you pick the three choices at the top. Now I'm about to hit this guy, and I get a Z-score of -1.1, which gives me a p-value of 0.257. Time for conclusion. Is the p-value less than alpha? Is 0.257 less than that one? Oh, not so good. So no. So this is not statistically significant. Oh, it would have been nice to get a statistically significant result. And then I could say, have you noticed that vegetarians are not very happy people? But according to this evidence, there is no evidence, right? It's not statistically significant, so we can't reject H naught. Do we feel comfortable about this process and how that you can basically do everything you need on the calculator? Right, proportion stories, right? Comparing two population proportions. Couple of things I just remember. If we go down to this fella and we just go through the same data, but I go to the bottom, Wouldn't that give us a lovely picture? And isn't a lot of your homework got a little picture like that, and you have to pick from 4 of them? And can you see, you'll pick the one that looks like that. And sometimes, very often, when you do this homework question, won't they ask you for lots of things, not just the ones I wrote down, but lots of other things? So can you, once I get there, can you see that I can get P1 hat is 0.6 and P2 hat is 0.65 and all the other kind of things that I might want to know? Right. So anything that you want will probably be in that menu. Scroll up or scroll down, you'll find it. Are we good?
Can I ask you a quick question?
Go for it.
So I'm doing something wrong on my calculator, because every time I've tried to get it to draw like this, it tells me error, invalid, DIM.
Yep.
But all my other answers are coming out right. So do you know
What's wrong? I do not know what's wrong, but I know how to fix it.
Okay.
Okay. So anybody who has a weird thing happen to the calculator, like their husband got to play with it, or their little kid hit some buttons, they can sometimes hit some weird buttons and do some weird things. I don't know what they do, but I know how to fix it. So here goes. You got your calculator handy?
Yes.
Right. Now, if you look really carefully on that plus button, I know you might not see it on this screen, but isn't there a thing called MEM, memory?
Yeah.
So blue button, plus. Now the one you want is number 7. What I'm going to do is I'm going to get your calculator and make it factory default. In other words, what it would be if you took it out of the box. And that pretty much fixes every problem. So I'm going to hit reset. Okay, boom. Now the one I'm going to do is number 2, factory defaults. Hit the button. It's such a dangerous thing to do that it's giving you a get out a free jail card. Do you really want to do it? It's saying. And if you hit no, nothing has changed. It'll be just like you did. If you hit 2, reset, it's now back to square 1. Okay, try drawing it now, because there's a backup if that doesn't work.
Okay, give me just a sec.
Sure.
Oh, you're amazing. Thank you so much.
Look, I'm going to get my
crazy.
wife in. I'm going to get a witness here. I'm going to get my wife in here, and you're going to say that.
But you have this recorded, right? You can play it back to her. Thank you so much. That was driving me insane.
Yeah. Again, I couldn't tell you what happened, but it happens more often than I'd like it to happen. It happens to me, and I'm thinking, did I hit something wrong? But if it repeats it, then I just go and I set it back to factory defaults. So what was my backup plan? Because imagine a test that you do that and it isn't fixed. Right. Backup plan. Go back into the memory. Go back down to reset. And then do you see the guy that's called number 1, all RAM? What this is going to do is going to flush your RAM. It basically is going to delete everything that has ever been put into any submenu. So no matter where your little kid got into a menu inside a menu and put in some weird stuff, right? It's going to clear it all out. So all RAM. Resetting RAM erases all data. It's kind of telling you, look, this is dangerous, right? But you would just go number 2, reset. For instance, do you know when you put your data in and it's L1 and then the next column it's L2, and we do that quite a lot when we do data? Have some of you ever lost L1? Right? That will fix it, right? What I just showed you. And so you can get your L1 back. And that just makes life easier, doesn't it? Because you don't want to adapt. So, but dangerous, if you've ever stored something and you don't want it to disappear on you, can you imagine a big question where you've wrote, 30 numbers into L1 and you think, I don't want to redo that? Then you probably shouldn't do this until after that question's finished. Because you did say you got all the numbers, right? You did get all the data, so you know that side was working. And then you should do it. Okay, are we cool? So if I said, here's a story about group A and group B and 40% like this and the other one's 42%, could we set up a hypothesis test? Could we get these two numbers in the calculator? Could we come up with a valid conclusion based on whatever they tell you up here? You feel good about that? Then we are leaving that guy. He is done. We have one more guy to do, and that's chapter 8, and we're well on schedule. So we'll get started in as much in 9 as I can, so that when you come next Monday, we'll finish off 9 if we have to, and then it's open to revision, questions about, how do you do this? Because I'm a bit rusty on it. Okay, let's do the difference between two means. There are going to be two flavors. One is sigma is known, and the other one is going to be sigma is unknown. Right, and I had a little mantra, I'm sure I've used it. If sigma is known, is it going to be a Z or a T? Sigma is known. Z or T? Z. Then it won't surprise you. If sigma is unknown, it's a T. Right? I'm only going to show you how to do sigma known. I'm not even going to try and show you sigma T. Trust me, you don't even want to know how to do sigma T when sigma is unknown, right? So I'll have a story, so that's fine. Put it over here. Let's suppose we looked at football players. This is one I used in my other class, and basketball players. And I don't know who this would be, a sports scientist or something, believes that the average weight of a college football player is heavier than the average weight of a basketball player. That's what he thinks. And so now he's going to see, is there enough evidence, and I'll do it very cryptically, that the average football player is bigger than the average basketball player. Not really knowing a lot about basketball, my kind of gut feeling is, because I'm making this story up, right? Aren't basketball players probably taller, but they tend to be quite lean and mean, right? They tend to be quite skinny and athletic, but not carrying muscle bulk. On the other hand, not all, but aren't there quite a lot of football players which are shorter than basketball players? Maybe not by much, but definitely more muscular, right? So they probably are heavier. So that's where my gut feeling's coming from, right? So he collects the data on 100 football players, and the mean weight is 230 pounds. It's probably kind of light, but aren't college football players generally a little bit lighter than their professional counterparts? In fact, when you get a job with the Seahawks, don't a lot of them end up having to beef up and muscle up, right? That's part of the game. And that the standard deviation of this sample of 100 was 15. And then they go and they do, for no reason, 250 basketball players, and they find that their mean weight was 219, and that their standard deviation was 5. Let's just talk about that data, nothing to do with the story. Sample sizes are different, doesn't matter. The method copes with that. And the reason for that is, can you imagine sometimes you can find more of one group of people than you can of the other? So, you do what you do. Would you agree that superficially the mean is bigger? So it looks like the evidence is pointing in the right direction, right? An average of all these 100 is 230 pounds. The average of this lot is 219, so that's good. Doesn't that mean that there's a lot of variation in the weight of football players. And this is a lot less variation. What do you think is going on here, from what I know of football players especially?
Are there some European people getting confused and thinking it's European football, not American football?
American football. American football. I have been Americanized to the point where I thought if I said football, you would be fine. But evidently, you are very Europeanized American, so I should have qualified that. Right. What this is telling me is that there's a lot of variation in the weight of American football players. And that's not a surprise, because if you're a football player, can't you be different positions? Aren't the ones that defined big, square, hunky guys? But don't you have quite lean and mean, run fast guys? And also, you know, different positions, different body styles, different weights. On the other hand, aren't most basketball players, you know, within the usual variation of heights? Isn't there a lot less variation probably? Because aren't all basketball players essentially interchangeable, right? They all do the same jobs, mostly, right? So that's kind of why I chose those numbers. So let's get started. The null hypothesis, and darn it. I went and said sigma is known, didn't I? Can I redo that and tell you that sigma 1 and sigma 2, the population, right? That's neat. Thank goodness I did that in time. Now, the null hypothesis is that the means of both groups are the same, right? So on average, American football players are the same weight as average weight as the, you know, the average weight of a basketball player. Now, in this story, aren't we looking for evidence that points in that direction? Football players, American football players, heavier than basketball players. You agree? So, we are going to do this one by hand. So that's step 1. Step 2, we're going to get the Z-score. Step 3, we're going to get the p-value. Step 4, we're going to do the conclusion. Even although the story and the data is quite different, don't you follow the 1, 2, 3, 4 of hypothesis testing? So, what on earth does the Z-score look like? It's this formula. The difference in the mean of the first group, take away the mean of the second, divided by the standard error. Now, when we did the proportion one, wasn't that standard error formula ridiculously ugly, right? The one with the p bar and 1 minus p bar. It was messy as heck. And this one is not anywhere near as messy, so I can squeeze it up here. Sigma 1 squared over n1 plus sigma 2 squared over n2. So I'm going to just do it over here because I need more room. So it's going to be the square root of 15 squared divided by 100 people in the sample plus 5 squared divided by 250 people in the sample. And this, of course, I do have to do in a calculator. So we got a square root of 15 squared divided by 100 plus 5 squared divided by 250. And we are looking at, I'm looking at 1.533. Does that look good? Just checking I'm hitting and wrong. It looks good. 1.533. So this fella here, the mean of football players. Take away the mean of basketball players divided by a standard error of 1.533. And let me do that in a calculator. Put a little bracket around it. I could do it in one go. 230, take away 219, divided by 1.533, and I get a Z score of 7.176. Okay, I know what's going to happen here. If you do enough of these, don't you get accustomed to Z scores that tell you stuff? Is it not a huge Z score you get? Agreed? What kind of Z scores are huge? Isn't anything bigger than 3 or less than -3 pretty rare, and are going to be significant? So I can tell right now that is going to be massively unusual, right? So let's find the p-value. The p-value is the probability that you get a Z score, in this case greater than 7.176. Why do I know it's greater than? You see that guy over here? I'll do a normal CDF on it. Second distribution, number 2, and we want 7.176, 999, 0, 1, and we are looking at, I'm not even going to write this guy down, I'm just going to leave him like that. Would you agree that would be, oh God, 0.12 more zeros, 36, right? Practically speaking, isn't that virtually 0? Good news. Is the p-value less than the alpha? And one day I'll remember to put alpha in the question. It should have been 1%. So is 3.6 times 10 to the -13 less than that guy? You're down to, and it is. It's a yes. This is statistically significant. So could we do a little newspaper or magazine article or whatever it was and say, hey, you all thought this was true. We've now got evidence to prove it is. American football players are heavier than basketball players. And we've done it using this hypothesis test. And anybody in the world who wants to look at this data, as long as you tell them all the information, they will come up with the same calculations and the same conclusion. And there is no argument, really. I mean, okay, you'll get people who'll argue about the world is round, right? You know, there are always going to be weird people who'll argue about everything under the sun. But normal scientific folk will not argue about this kind of information. But there is possibilities that by sheer bad luck, couldn't this sample just be a little bit wonky? And it's not true. Because it's, isn't it, the general truth is, we never tell you something's 100% certain in statistics, right? If someone says they're 100% sure of something and they're a statistician, they're lying to you. We don't really know 100%. Don't we qualify it by saying, well, there's a 1% chance we're wrong, right? Significance level is essentially saying that, right? Or there's 1,000,000 to 1 chance we're wrong, or in this case, probably more like 1 billion to 1 chance, right? But there is a chance, isn't it, that we got it wrong, right? And especially, that's not too bad. That's pretty decent numbers, not great numbers. But you know, if you do a sample of only 10 of these guys and 25 of these guys, can you imagine we did a sample of only 10 American football players and 25 basketball players? Shouldn't you just, for common sense, not for the statistics, but just common sense, shouldn't you be a bit wary of any kind of results? Just based on the common sense idea that, you know, you could get really weird answers when you ask 10 people. Couldn't you just get 10 linebackers? Right? Or 10 quarterbacks. I mean, I'll try to pick different extremes. Right? So, we are good. You like this new process? Wouldn't you like to do it on a calculator? So you know I'm going to show you it, right? So, it should not surprise you where this guy, this hypothesis test is hiding. Isn't he hiding in stats tests? Now, sigma is known. Z or T, what do you use?
Z square.
Right? So that means it's number 3. Now, when I hit number 3, do you see I have 2 choices? One is data. So that's going to be the stories where they tell you, here are the weights of 10 American football players, and here's the weight of 20 basketball players, right? They just tell you the numbers, right? They don't tell you this data, which would be much easier to deal with, right? They just tell you the numbers. Of course, they'll tell you that because sigma's known, right? And off you go and you do your thing. But in our particular story, wasn't it stats? We were given the information, the statistics. So here is how it goes. Do you see it's kind of pretty obvious what goes where? Won't sigma 1 be 15? And sigma 2 will be 5. And X bar 1 is 230 pounds, and there were 100 people in that sample. And why did that say 1? This guy here is 2. And the sample size was 250. And we are looking for mu1 greater than mu2. So won't that be the one at the end? That guy. And then I should come down and I should be able to hit calculate. So here goes. And did I get a Z score of a similar size to the one we did a few seconds ago? 7.71. I can't remember where my piece of paper is, but wasn't it something like 7.2 or whatever? Definitely in that ballpark figure. And didn't we get a ridiculous e to the minus 13 when we did it by hand? And these may be a little bit different, rounding off. Now, do you see the kind of stuff that you get for free? You know the means and you know the sample size. I don't think that's for free, actually. I knew what they were, but they tell you anyway, right? We feel cool about that question, right? So if sigma is known, so that's the only time I'm going to show you it by hand. So let's do a story where we just use the calculator, right? It's going to be a lot quicker as well. I'm trying to figure out where I put my calculator here. I'll put it here. Okay, I need a different story. What shall I do? IQs. Since I'm in charge of this story, I can make any data up I like. So we had IQ of Scottish people. That's going to be group 1. And group 2 is going to be the IQ of some French people. And someone thinks that the average IQ of Scottish people is greater than the average IQ of French. So we're trying to prove that Scottish people have an IQ that is greater than the French. And we're going to do it at the 1% level. Only this time, I'm going to tell you how we did it. We did a sample of Scottish guys. So we randomly selected a number of Scottish people, and the IQs we got were 102, 107, 103, 95, and 112, right? I'm keeping my sample sizes really small. Can you imagine in real life that might be 500 people, but I'm not going to do 500. And then they go and they get a random sample of French people, and they got the answer 102, 108, 104, 101, 97, and just by coincidence it was 5 French people, right? And we happen to know that the IQ standard deviation is 10. IQs are 10, so that's actually pretty realistic, that bit. That is. So we are ready to find out, is there enough evidence to prove that Scottish people are cleverer than French? And since I'm in charge of this story, the answer better be statistically significant and a yes, right? That's the way it should go. But I might end up not getting that. So the populations are the same. Or Scottish people are bigger than French. I've just realised all my questions are bigger than, do you know that I could have, too late now, but couldn't have done a less than, it wouldn't have made a lot of difference, right? Wouldn't matter. Okay, I'm pretty much ready to start getting the calculator to do this. And I'm going to go over to data. Bump. Now, IQ standard deviation of Scottish people is 10. IQ standard deviation of French people is also 10. And guess who has forgotten, because I keep doing this, haven't I forgotten to put my data into L1 and L2? So get out of there, hit number, edit, and now put the data in 102, 107, 103, 95, 112. Kick over to this side, 102, 108, 104, 101, 97. Do you think I'm probably going to get not statistically significant here? It's going to be a close thing, I'm guessing. Now, if I really wanted to, shouldn't I have made them all 120s and 30s and make them all 70, 80s? That would kind of guarantee it. So we got our data in. Back to the question that I had a few minutes ago, but now I can do it. The good news is it remembers where I left off, so I don't need to redo it again. 10 for Scottish standard deviation, 10 for the French. Data is in L1, data is in L2. Frequency, leave it alone. Frequency, leave it alone. We want to see, is it greater than? That's this choice. And now to do calculate, go. Oh dear. 0.22. And the p-value is there's step 1, there's step 2, there's step 3. Conclusion time. Is the p-value less than alpha? Is 0.41 less than 0.01? The answer is no. Not statistically significant. So I can't boast about how intelligent, more intelligent Scottish people are than French. Do you know I should have cooked the data better? But what you should do if you're a real, if you let the data talk, you should say, hey, at least in this sample, there's no evidence to say there's anything going on. I can't tell. Right? They might be cleverer than me. I might be cleverer than French people. We might be exactly the same. Nobody knows. That's it. Not statistically significant means you know nothing, right? It doesn't mean that I've now proved that they're the same. Just because I couldn't prove that they were bigger doesn't mean I've proved that they're the same. Are we cool with that guy? So if you have a hypothesis test comparing the means of two groups, this is basically how you do it by calculator. Now, I did say that there were two versions of that. We've just finished doing sigma known. There's another version called sigma unknown. I am not even going to try, as I said, to show you how to do that by hand. Trust me, you do not want to know. If you really do want to know, go and look at the textbook and see what happens, right? It'll tell you. So all I need is a little story, and we'll show you how it works. You can have, let's do two groups again. Let's group 1, group 2. Who should we pick this time? I'm running short of things to make up stories about. I'll do what I've done with the other class. A zoologist is studying various animals. Maybe he's studying big cats, right? So he decides he wants to look at the weights of an adult male mountain lion and the weights of an adult female lion. And he thinks that their average weights are different. He's not 100% sure if males are bigger than females, which happens in a lot of species, but not all species. Do you know there's some species where the female's bigger than the male, right? That happens too. He just thinks that they're different, right? So what we're looking for here is male not equal to female. And he wants to do it at a significance level of 0.1. And so he collects data on 100 male mountain lions, and he finds out that for that 100, the mean is 135 pounds, and that the standard deviation is 5 pounds. And for the females, he collects a sample of 200 of those, and he finds that their weight is 131, and that the standard deviation of this group is 2. So if I'm looking at this data, raw data, what that is telling me is that male mountain lions have a big variation in weight, right? There's some really big ones, but probably some really light ones. And this standard deviation is much smaller. Doesn't that say that most female mountain lions are kind of about the same weight, right? Give or take a few pounds, they're about 130 something, right? For male lions, it's about 135, but they could be really big, you know, 150, or really light, 120, right? A lot more variation. But we got everything. Let's get the calculator. Okay, let's not. Let's set up the hypothesis test, then we'll grab the calculator. We'll assume that the null hypothesis is that they're equal, right? Average male and average female, they're about the same weight. The alternate, because of the way that this was phrased, is that one. Isn't that a two-tailed test, right? I just want to prove that they're different, right? I want to say male mountain lions are different weight than female mountain lions. Now, I could look at this data and say, wait a minute, you already know now that it's 135, right? But normally you're meant to make this up before you even look at the data. So before he ever collected one piece of data on the weight of mountain lions, he was thinking to himself, I'm pretty sure they're different, but I'm not 100% sure I know which way. So that would be this hypothesis test. Now we can do the data, and let's see what we get. It's in stat. Have you noticed that there is no mention of population or sigmas in this story? That means sigma is unknown. Yeah, you told me standard deviation, but that's not population, right? That's not a sigma, it's an S. So based on that, which one of those guys is going to be the one that we should use for the two samples that we're dealing with? And you see, pointing at 4, do you agree? Two sample. Why is it a T? Sigma is unknown. Get the gist? Sigma known, Z. Sigma unknown, T. I mean, that's a little mantra. Just if you're thinking left or right, 1 or 2, you know, that kind of, I'm not sure which one to pick. Sigma known, pick the Z one. Sigma unknown, pick the T one, right? And that'll get you through that hassle. Now I'm about to hit that, and let's see what we got. Now in this question, it's either data or stats. Do you see that choice? Can I move this over a little bit there? Data or stats. Based on this information, isn't this a stat story? I'm telling you statistics. See if I went and said, here's 20 mountain lions, there's all their weights. Here's 20 other mountain lions, here's all their weights. That would qualify as a data, right? So I'm going to go over to stats and hit it. And here it goes. I got a little bit distracted because I'm looking at the screen and looking at the buttons. Males go first. In the males, the average was 135. The standard deviation of the sample was 5, and the number of people in it was 100. For the females, it was 131. The standard deviation was 2, and the number of people in that sample was 200. And we are looking at the not equals to choice. You see that's choice number 1. Right, the first one of the 3. Now here's a question you might not expect. Pooled, yes or no? If they tell you in the story, and they have to specifically say this, we do not know what sigma is, but somehow we know that they're equal to each other, then you will choose yes, pooled data, right? If they don't mention a darn thing, and they never mention sigma, which I never did, you are going to go no. So you'll never say yes unless they specifically say, we don't know what sigma is, but we believe they're the same thing, right? Or a phrase akin to what I just said. So probably no is going to be your answer 9 times out of 10. Then I'll scroll down and we'll do a calculate, and boom. And we got a test statistic, which is basically your T guy, of 7.7 and a p-value of 5.2 times 10 to the negative 12. Wow. I'm going to have to make these numbers closer to each other so we don't keep getting really extortionate ones. Can you see that p-value is basically telling me my conclusion, but I'm still going to write it down. Isn't this going to be statistically significant? Tiny, right? So here goes. Is the p-value less than alpha? Is this guy less than this guy? And the answer is yes. So this is statistically significant. And when we go back and look at the data, couldn't we say, it looks like mountain lions are on average going to be heavier. Male mountain lions are on average going to be heavier than female. Right, just looking at the raw data. Right. This just says that we know that they're different. When you look back at the data, I guess you could probably decide on which side of the different are the in. In this case, I would say the evidence is saying it's males. I don't think the difference is significantly, oh God, I've used that word now. The English word significant, right? I don't think the difference is important. Would you agree that 4 pounds is probably very negligible between the two species? Now, there are some species where the difference is like the males are 50% heavier than the females, right? And that would be quite an important difference. Suppose I did this and there were ½ pound difference between the two. Wouldn't that be, makes no darn difference at all. If you saw an animal at a distance and you knew what its weight is, you probably, unless there was other reasons, you probably wouldn't be able to say it's a male or a female. You know, they're about the same weight. Are we cool? So I want to do a story, sigma unknown, but a data version, right? That way we've covered all the possibilities. And then we'll have a look maybe at the homework to see what that looks like. Okay, got this guy, clear it out of the way. So group 1 is going to be stats students, and group 2 is going to be English students. So now I get to insult English students, but you're all stats students, so you're all not going to get insulted, right? We're going to insult the other group. So now I have to figure out what to insult them by in my made up story. So I'm not sure an insult is the right word now, because I can't think of anything particularly bad about them. Totally no idea where this came from, but it's a well-known fact that statistics students are just taller than English students. I mean, it's just known, right? If you go into a class full of English students, aren't they just kind of small people? And you go into a class of statistics students, they're really big people. You didn't know that, did you? Right? Because I just made that up right now. So in this alternate universe, we believe that this is true. And I'm going to change that. Can we pretend that stats students are actually shorter than English? Because I want one story where it's pointing the other way, because I keep pointing bigger than, right? So we believe that statistics students are smaller than English students in height. And we're going to do it at a 1% level. And we are going to do the test based on some data. So we go and we find some stats students, and we find out that their heights are 63, 61, 65, 61, 63. So we got 5 of them. And we got some English students, let's pick 6 of them just to be different. And they were 64, 61, 64, 62, 66. Oh, I need one more. And 67, right? And the question is there enough evidence to prove that on average statistics students are less tall than English students, right? The null hypothesis is that their average heights are the same. Since the way I've decided to describe my story, don't we finally get a left tail test?
Can you move your paper to the left a little bit?
Left. Can you see it now?
Yes.
Okay, so actually I'll move it way over to the left, so I can have my calculator now. So that's step 1. Step 2 is going to get me my t-score, and step 3 is going to get me my p-value, and the last bit is going to be conclusion time. Okay, so we kind of know how these stories go, don't they? They're just same old, same old. So let's hit start and go into edit, because this time I remembered that you have to put the data in, right, before you can continue. So statistics, there were 63 inch, 61, 65, another 61, and finally a 63. And over here we have a 64, a 61, 64, a 62, 66, and 67. I think it's going to be a near miss here. It might make it, might not. We'll see. I'll go start. I'll go over to tests. Would you agree nowhere in this story did I tell you sigma? So this is definitely the T fella. And the 2 proportion to 2 sample t-test there. And when I now cross over to data, hit enter. And it's mostly set up for us. Isn't stats people in L1, aren't English people in L2? Isn't this 1 and 1? And we are looking for choice, the middle one, right, this one. Again, I'm picking no. I mentioned nothing about, I don't know the standard deviation, but I know they're the same. So I'll say no. And then I'll hit calculate. And I get 1.17. And I get a p-value of 0.136. So is the p-value less than the alpha? And the answer is no, not statistically significant. So I can't say that stat students are smaller than English. I haven't proved it. Now, can you imagine in a different world that might be 0.005, in which case it would be statistically significant, and then I'd say stat students are definitely less tall than English students, and we'd call it good. Would you agree that what we've done so far today has got a flow to it? That you basically, if you stick to the 1, 2, 3, 4, whether you do it by hand or probably more likely when you do it by calculator, as long as you choose the right menu and put the data in the right place, you're probably not going to be unstuck. That's what I hope you've got. So what I'm going to do right now is look at some homework questions just to make sure that I've covered all the bases and I haven't skipped or missed something that might be important. Okay. Oh, right off the bat. Do you see how one of the questions is pick the picture? Did I show you the draw feature on the menu that draws the picture so you know which one it is? Oh, good, right. So you just hit, you go back to your guy and you go to, not calculate, you move over to the next one, it says draw, and it'll be one of those 4 pictures, although you could probably calculate it yourself. Okay, so these guys are all proportion ones. Where am I going? Okay, this one is as good as any. Is the national crime rate really going down? Some sociologists say yes. They say that the reason for the decline in crime rate in the 80s and the 90s is demographics, which is just a fancy way of saying population distribution. So here's a fact. Do you know that more 20-year-olds commit crimes than 80-year-olds? Right? Would you say that's probably a truism? Do you know the main age group for committing crime, for crimes that will get you in jail, right, is roughly 18 to 30. Right? So if you look at our prisons and you look at who's in our prisons, you'll find 18 to 30s is by far the biggest age group. So if our country is getting older, do you see there's fewer of those people? So there are going to be fewer people in jail. That's what they're saying. So it's not, well, I don't know. That's what they're saying the main reason is. I can't argue about it. So it seems the population is aging and so fewer crimes. Makes sense. According to the FBI and the Justice Department, 70% of all arrests are 15 to 34. Well, okay, I give you my numbers, but that's in the same ballpark, isn't it? Suppose you're a sociologist, Wyoming, and a random sample p-file showed 35 arrests last month, 26 are male, I found in 10% level. Now, can I just check that that's the right homework? Because that looks like it's 8.3. It is. 8.3 just has the old data compared to the new. So let me zoom over and find an example of 8.5, which is what we've just done. It'll look very similar, but there are differences as well. Gotcha. Right. Now, going to stop sharing, going to go in and reshare. Gotcha. Okay. If you're really good at memory, which one of these ugly formulas is the formula for getting Z-score?
We can't see.
I can see it, so what's the problem? Let me draw it out one more time. I'll go out, I'll go back in, I'll hit screen 2. Can you see it now?
Yeah.
Okay. Question 1. This is 1B. Which one of those ugly formulas is the one that gets you the Z-score? And if you root back really carefully at your notes and you wrote it down, I did do it. Remember the one question we did by hand? We'll call it 1, 2, 3, 4, and 5, right? 1, 2, 3, 4, or 5. Which one is the guy that does the job?
I might be wrong. I want to say it's number 1.
Close, but you're wrong.
Fair enough.
But you got half of it right, so don't feel too badly about it. You're almost there.
Isn't
Which
it-
one? Yeah, it's 2. And play this video and stop at that page and you'll see that I wrote it down, right? And in a question like that, wouldn't you probably rush over to the textbook and have a quick scan through it, you thought, right? So let's skip by all the, the pick a choice thing, because that's really what that is. And let's look at this story. A random sample of 49 measurements from one population had a sample mean of 14 and a standard deviation of 5, and an independent random sample of 64 measurements from a second population had a sample mean of 17 and a standard deviation of 6. Test the claim that the means are different and use a significance level of 1%. So let's break this down into smaller questions. Is this going to be a proportion question, a difference in proportions, or a difference in means? I see Stacey saying difference in means. Agreed? That wasn't a hard decision. Now, in this story, do they mention sigma? And it has to be sigma, or at least the Greek letter sigma equals something. Does it mention that anywhere? So is this going to be a Z or a T when we put the numbers in?
T.
T. So you know you're going to do the 2 sample t-test, right? Agreed? Did they mention anywhere in this story that we don't know what they are, right? But we know they're the same, right? We don't know what the standard deviation sigmas are, but we know that they're the same, right? Is that going to be pulled, yes or no, because of that? Because when you go to that menu, there's going to be a bit at the bottom where you says pulled, yes or no, and you have to pick one, and you have to pick the right one. So does it mention anywhere in that story, we don't know what sigma is, but we know they're the same? Didn't mention it, agreed? And when they don't mention it, what choice do you pick? No, right? No. Okay, plug in your data, get your answer, off you go and do your stuff. So in this story, they want to do the claim, are the population means different? You see it's right there. Which one of these 4 dots is the null and alternate to population means are different? Is it number 1? Is it behind door number 2, 3, or 4? Someone is pointing at 4. Is Stacey correct at pointing at 4? No one's backing Stacey up here. Stacey is correct. It is 4. Right, now it goes in and asks you to compute that, and then compute this, and compute this, and compute this. Do you know all these numbers will come from your calculator? Do you know if you put the data in? When you look at the data, it'll tell you X1 bar and X2 bar. Won't you just have to subtract them so you can put it in there? So let's say X1 bar is 40 and X2 bar is 50, right? You'll do it that way. Now, when they ask you to compute the corresponding test statistic, right? That's their phrase. What I would have probably said is tell me the Z score or tell me the T score, right? In this case, it's tell me the T score. Now, this D would probably have, if I was doing this, a box, and you would type in what the p-value is, right? Nothing point nothing 22 or 1.7 times 10 to minus 9, right? Whatever that is. In this case, they give you a range of values. So let's just pretend we did it and p-value was 0.12, right? 0.12. If it was 0.12, wouldn't you pick that one? It's between those ranges. If it was 0.6, 0.6, where would that go? It would be that one, right? So do you see that they don't ask you to give me the p-value? Don't they just give you an interval and you look at your p-value and you put it in? And with the last class, I think I know why that's the case now. Some people who do this will be using calculators to do it all. And some, like we would probably do it. And can you imagine other people are going to use, do it by hand? God forbid the poor souls, but some would. Do you know some people will use other software like Excel? Every time you do that, aren't you going to get a slightly different p-value because of rounding off issues? So I think they've done it as an interval to kind of, you know, you just need to pick the right interval. And no matter how you do it, you're all going to agree at least on the interval. And that's what it does. And then a couple of conclusions and a couple of interpretations. So they're asking the same basic information, right, do a hypothesis test. You see they just break it down a little bit differently, but everything that you need to know is on your calculator. Daniel, did you do that question just out of curiosity? Is that what you were trying? If I'm not picking on you too much, what was x1 bar take away x2 bar? Have you got that yet?
So I did it, my homework has different numbers, so I did it with the homework to my numbers.
Oh, okay, so your numbers won't be those numbers, but was it relatively easy to find the numbers that you needed to fill in that answer? You know, wasn't x bar, x1 bar and x2 bar in the data when you did it. So you just subtract them and you got it. Once you've done one of these questions, can you see that they just basically change the story and they give you another one? Well, I'm picking on you, Daniel, because you're just handy. Have you done most of these guys already or just some of them?
This is the first one.
First one, okay. So I was going to say, did you notice that they're pretty much the same? Okay, let's look at 7. The thing that strikes me about 7 that's really important is you see that they tell you sigma. Okay, do you also know that they're talking about means? So when I go looking for which of the many menus I could be using, wouldn't I be using a 2-sample z-score? Why z and not t? I know sigma. But apart from that, won't it be pretty much the same question? If I move on and we do this guy, do you see this is more like the football and basketball story? Do you see that you've now got the data, right? It's 2 sets of data. In this story, is there any mention of sigma? None. Wouldn't that be a 2-sample t-test, right? The t-test. And won't you go to your calculator and put all these numbers in L1, and then won't you go and you'll put all these numbers in L2, and then everything pops out. Now, what is everything? When you do these questions, don't you get all of these on the screen? You don't just get the Z value or the T value and then the P value. Don't they tell you X1 bar and S1 and all that? So you basically go to your calculator and you say, I'm making these numbers up. That guy's 12, that guy's 25, that's 3, and that's, you know, whatever. Oh God, I'm not even hitting enter, right? Okay, that guy's 12. Well, you can't hit enter, you have to do it one at a time. That guy's 13. What are you doing? Oh. Evidently, I've just got every single question wrong now. I think the reason is for some reason that was on. Okay. Okay, we're back to that guy. I'll probably not do that because I'll screw up again, but can you imagine you just write down the numbers and you're good to go. Okay, so that guy's 12. Let's try it then. That guy was 14. Okay, that guy was 25. That guy was 36. What's the level of significance? I don't even know why they got that question because it's silly. Because didn't they tell me over here what it was? One of these would be the storyline. Do you use a T or not? What's the sample thingy? You get that in your calculator. One of these and that picture or whatever, right? I'm very cryptic here. I'm not even sure I'm helping because I think it's one of those things that's a doing thing, right? You can't really talk it through. But can you imagine doing this question the way that we did the one in class, right? So if you just stop that video and look at what I did, if you follow those instructions, same thing's going to happen with all these guys here. Can you see that we're now moving on to proportion questions? But same basics, same storyline. And you're finished. I guess I'll find out on Monday whether or not I zoom through that too quickly. Do you feel that you understand the process of comparing two means and comparing two proportions? And you just have to figure out, given what information, which of the menus you go into to get the guys that you want. We go. Last chance. because I'm about to start the next, well, I'm not actually about to start the next session. I think we need a 5-minute break, don't we? And then we'll start the next session. Okay, I'll see you back here at 7. Have a break.
I'm finishing up my master's degree, and so it's the last week, and it's just a lot. But we're almost there, almost done.
You're finishing off your master's at the same time you're taking this class?
Yeah, I didn't need this class for my master's degree, but I need it for my ASHA certification, just a different license. So.
Okay, so do you want to share what I don't need to share is what your
Yeah.
master's in?
Yeah. So I'm going to be an SLP.
Oops.
Sorry, that's my dog.
Right, try that again.
Yeah. So I'm going to be a speech therapist.
Oh, okay.
Yeah.
That's cool.
Yeah.
And so I'm assuming that you need the statistics because in your job, nothing stays the same in the medical field, that you have to be able to look at, you know, new evidence on better ways to do things and be able to look at it.
Yeah, definitely. And this has been really relevant because we look at different research articles all the time, and we have to look at p-values and
And now you know what the damn things are.
yeah. So yeah, it's been good.
So in the past, when you looked at p-value, did you just kind of know small was good? Or did you not really know what that was
I
talking
think
about?
it was as long as p was less than 0.5.
Okay, so in your
But the
world,
native-
5% is the magic number.
Yeah.
So 10%, nobody ever does it in 10. Do anybody of them ever do it in 1? Just curious, not that you know or remember.
Not that I know of.
Okay, so as long as it was less than 5, they were cool. So when they come up with something like that, is the kind of, I'm just trying to get into that your field, is the kind of thing, if something important comes up and they says, this is a better way of doing it than it used to be, and we've got this evidence, other people will check it out and try it, and they come back and they do a kind of backup report saying, yeah, we've done this in 10 different places and we're getting the same kind of successes that that first person said. And then you read it and you say, okay, that's how I'm going to do it as well now.
Yeah, basically, more or less. Yeah, for new treatment options.
Right. So
What's
so you're always
successful
looking.
and what's not.
Yeah. So you're always looking, and so who's the main people that do research? Is it in universities that they? Because that takes money and time to do that. So it's not the kind of thing that you could probably do on your own unless you got a grant.
Yeah, not me. Not me. Yeah, it's a lot of. Sorry, my dog got me. Yeah, a lot of professors at the college who have either been teaching for a really long time or I don't know. There's so many different researchers.
Is your dog growling now?
Yeah, so my dog is the best, but as soon as I start to talk on a phone call or a Zoom call like this, he decides he needs all the attention. And
Well, because you're not paying attention to him, right?
I know. But as soon as I'm quiet, he's going to go back to sleep. But as long as I'm talking, he just thinks he needs all the attention. So.
Well, I have a dog that's in my room right now, and it's a cutie. My dog is sleeping right now. If I get up, which I'm not going to, but if I get up and walked out that room, she must have radar ears. Because if I leave the room, it's obviously because I'm going to get some food. So if she follows me, she might get some.
Well, obviously.
That's their mindset. They are cleverer than I am. Animals are, yeah, they know how to manipulate me really well. Okay, guys, let's get started. Last chapter. I always think last chapters is kind of sad. I got this from my other classes as well, because we're going to be saying goodbye in a little while, right? We've got this little class that I've been insulting and telling bad jokes to, and now you're going to leave and do some cool stuff with your careers and whatever. But yeah, let's go off that depressing thought. What's chapter 9 about? It's going to be about a thing called linear correlation. Only 2 sections. Kind of interesting. We're leaving the world of hypothesis testing. That's gone. Don't forget it, but it's gone, right? What we're going to do now is not going to have any relevance to that, right? It's a new thing. So we'll start off with what's called the scatter diagram. So imagine that you collect data, and the data is always the same format. It's 2 variables. In this case, it's the height of a plant and how much it weighs. So maybe it's an edible plant, right? So the more it weighs, the more you'll be able to sell it on market for, right? Whatever the reason you do it. And in this case, 8 inches weighs that amount, 12 inches weigh that amount, 16 is that. That is just a sample of what, 5 plants, right? A scatter diagram, you have an x-axis, which is always going to be the top. In this case, it's going to be the height of the plant. And then you have a y-axis, which is the weight. And then you plot points, just like you would do coordinates. So I guess I'm going to have to figure out a decent scale here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh God, keep going. 11, 12, 13, 14, 15, 16, 17, 18. Whoa, just made it, right? 19. And going vertically, no, I don't need to, only need 16. Going vertical upwards, I need 19. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay. A height of 8, weight of 6. Height of 8, 2, 4, 6. Height of 10, weight of 9. Height of 10, weight of 9. Height of 12, weight of 13. Height of 15, weight of 17. And lastly, height of 16, weight of 19. Now, could you pretend I did this really neatly on square paper? Right. That's what's called a scatter diagram. Now, when you plot, in this case, height against weight, you very often find that the data is not perfect. It never is in real life. It's not a perfect straight line. But would you agree that it's roughly linear? Yeah. If I put that little line through it, does it help you see the linear? So we would say that this data is linear. And the process of plotting all the dots is really just, isn't it, like coordinates? And you've got the scatter diagram. So this gives me some information about the connection between height and weight. Would you agree that the taller a plant is, the heavier it weighs? Isn't that being reflected in this picture? Would you agree that very roughly that these set of dots are almost in a straight line, so they're almost linear? And we also like, when we talk about scatter diagrams, we like to talk about how good a fit it is to being a straight line. And we're going to be quite vague here. It's a strong fit, it's a moderate fit, or it's a weak fit, right? Me personally, and there's a little bit of a judgment call here, I think that's a pretty strong link, right? Do you agree that set of data points are pretty linear, right? Strong connection. If you want to see what I would consider strong, would look not perfect, right? But kind of pretty straight, right? Weak linear wouldn't quite be as good. I mean, it's still linear, right? But there's a lot more up and down going on. And something that would be weak would be a situation where it's probably linear, hard to tell, but even if it is linear, would you agree that those dots are pretty much all over the place? So strong, moderate, weak. So, strong, moderate, and weak. So that would be one term that you'd use, right? I don't know, I'll put it here. Linear. Curved. Random. Can you imagine a scatter plot where the dots are just totally all over the place? That'd be random. Would you agree that it's not perfect, but isn't this mostly linear, right? It looks kind of straight. Would you agree in this case, it's got more of a curve through it? In this case, it's much straighter. So if you're describing in words a scatter plot, you can talk about it being linear, curved, or random. If it is linear or curved, then can't you talk about it being strong, moderate, or weak in that shape? So can you imagine you could have it curved, but the dots are much more vague, right? That would be moderate or weak. Right. Now, since I got this, we can talk about positive, which both of these are. Oh, by the way, random pretty much is the end of the line. If you do a scatter plot and the data is random, doesn't that basically mean the first thing has got nothing to do with the second thing? It's a bit like me having on the x-axis your age, on the y-axis how many coins in your pocket, right? There's no connection. And so random doesn't really get much credence because you can't do anything with it. Now, these are called positive. And what is positive? If we call this x, which is, if x gets bigger and the y gets bigger, it's positive, right? So it's going uphill. But can't you also get linear data that's going this way, right? It's still linear, right? But this time we call this negative. And can't you have curved data? Probably haven't given myself enough room to be very curved. But can't you have curved data that is also negative? So if I tell you I have a scatter diagram and it's positive and it's linear and it's strong. So I'm just telling you those three words. I have a scatter diagram and it's positive, linear, and strong. Have you got a kind of mental picture of what it would look like without the specifics of the number, right? Wouldn't it look something like this? Positive, linear, and strong. If I said it was negative, moderate, and curved, negative, moderate, and curved, couldn't the data look something like this? Can you see the negative, the going downhill? It's not as tight, so I would probably call it moderate, and it's certainly curved. So what we're just introducing you to here is the vocabulary of how you could describe a scatter plot. You would describe it by linear or curved. You would describe it by strong, moderate, or weak. And you could describe it by using positive or negative. If you put those three terms together, do you see you get a pretty good visual picture of what something would be without knowing anything except I just told you it was linear, positive, and strong. So it's a cool thing, you know, right? So we are going to focus on one situation. Linear scatter plots. Now, if you enter into the scientific world, you'll find that there is lots of data that are linear in nature, right? You've got two variables and one of them relationship to the other is linear. But you'll also find that the relationships can be quadratic, exponential, logarithmic, and all sorts of fun stuff. So linear scatter plots. Right, so let's have a look at what that might be. Okay, describe that one to me. Give me any of the three terms. Well, I'll give you the first one that's linear. Give me any two that's left. Say it again.
Is strong and positive.
I would agree. Agreed? Cool. Now, right now, I am going to give you a magic number and not tell you where it came from, but I will tell you later. So you'll find out tonight where it comes from. And it's a number called the correlation coefficient. Now, correlation coefficient is little r and is a number that always takes a value between 1 and -1. And what this magic number is, that for any scatter plot, now you've got to remember, see all these dots? They came from a table of numbers, right? They came from a big version. I can find my table, which I probably won't be able to. It's under here. Yeah, can you imagine a big table like that with 40 different points in it, right? So it came originally from this table. We use these numbers and we will get a magic number, which the calculator gets for you. And it's called the correlation coefficient. And it always has a value between -1 and 1. So let me show you the extremes. If the R value is 1, it's the strongest linear you can ever get, because the data is on a perfect straight line. That would be a correlation coefficient of 1. That ain't going to happen much in real life, but you know, theoretically it could happen, right? A correlation of -1, a correlation coefficient of -1 would look at that. Now, can you look at those two? Can you see that it's a perfect straight line going up and a perfect straight line going down? Agreed. If I tell you I have a linear scatter plot and I tell you that the slope of the line that goes through it is positive, isn't that the word we use to describe it? We say it's positive. And see, if you do a line through a scatter plot and the dots go downhill, don't we call it negative? Isn't that the slope of the line? Do you see why the word positive and negative kind of has a sensible meaning? Have you noticed that the correlation coefficients match that perfectly? +1, positive slope. -1, negative slope. If I told you I had a correlation coefficient for this guy and it ended up being, say, 0.9, right? Just magic, I'm telling you it's 0.9. Can you tell, even if I never gave you the scar diagram, that it would be positive and linear and strong? Positive, because R is positive, right? Strong, well, would you agree 0.9 is pretty close to being 0.1, right? Pretty good. Linear is kind of obvious because they are linear. So what do you think, right in the middle, a correlation coefficient of 0 would look like? What kind of scatter plot would that guy look like?
Would it be random?
It would. It would look like somebody got a shotgun and just shot it a couple of times with lots of pellets. Would you agree if that was my data set? Wouldn't you be hard pressed to draw a direction through it? I mean, is it negative? Is it positive? Yeah, you can't really tell. That's what an R equals 0 is like. So I haven't told you where it came from. You don't need to know quite yet what it is like, right? But you can guess that this R value is going to tell you quite a lot about the direction of the line, and the value of it is going to tell you a little bit about whether it's strong, moderate, or weak. Now, between these three guys, there's lots of other numbers, but for instance, wouldn't 0.9 be pretty strong? Something like 0.2, wouldn't that be pretty weak? And something kind of in the middle there, say about 0.7-ish, wouldn't that be kind of moderate? And the closer you get to 1, doesn't it get stronger? And the closer that the R value gets to 0, doesn't it get weaker and weaker? And so you can use that to answer this interesting puzzle. Here are 3 scatter diagrams. One of them is 0.8, one of them is 0.6, and one of them is 0.4. You should be able to match picture with correlation coefficient. Even if you don't know where it came from, you can tell, can't you? Okay. Which one of these 3, I guess I'll have to call them names. That's A, that's B, and this is C. Which one of these 3 is a 0.8?
B.
Right, because it's the best of the 3, isn't it? And would you agree B is the strongest of the 3? Who is 0.4? Which one is 0.4? A, that's what I see moving. Would you agree that 0.4 is the weakest of the 3? Right, that's kind of vague, isn't it? Still probably linear. Done. And that one, 0.6. So let's see what we've learned. If I gave you some data in the form of a table, that guy there, could you plot it and make a scatter diagram? I hope you could. After you've done that scatter diagram, could you use words like strong, moderate, and weak? Would you feel comfortable about that? Could you use positive or negative in linear or curved? Would you feel comfortable about that? So if you draw a scatter diagram, you've got some vocabulary. If I gave you 3 to pick from and I gave you 3 R values, would you be able to at least have a reasonable guess at which one would match which picture? Now, when you use R values, correlation coefficient, well, you make sure that we're really talking about linear. In fact, we're pretty much, everything's linear, right? Theoretically, they're curved and things happen, but we're just going to focus only on linear scatter plots. Right? Are we good? It seems to be going good. Would you agree it's totally different from hypothesis testing? It's very visual, quite different in lots of ways. So I am going to see, hold on a second here. I am going to see, or we're going to see, the beginnings of what the homework looks like. Because sometimes the book has to do things in a particular way. And so here we go. Right, are we looking at homework 9.1, Scar? Right. Describe the relationship between 2 variables when the correlation coefficient R is one of the following. If it is near -1, right? So if R is a number close to -1. 1, 2, 3, 4, 5. Which one of those 5 would be the description that you could give? So strong, negative. I think it was Courtney that mouthed 1. Would you agree? Right. You can go like this as well. Right? Because I know you just don't like talking. Okay. If you were near 0, I see a 2. Do I agree with a 2? Weak or not linear at all, right? Just random, right? And you're saying 3? Oh, are you answering this one? Okay. So in this one, strong, positive, and linear. Great. Right. Now, that was fine. I think that's a pretty reasonable way of asking that question. Sometimes they do things in a kind of back to front weird way, but I think that was clear. Right. Here are some pictures. Scatter plot. Whee! Scatter plot. Scatter plot. Look at these diagrams, and which diagram shows high linear correlation, moderate or low correlation, or no correlation at all. When they say the word linear correlation and they say no linear, they're saying it's not straight, right? Just phrase, that's what they're saying. I would probably say curved, but not linear, I guess, counts as curved, right? So if I was doing A, moderate or low, high, or it just ain't straight. Right, I'm picking moderate only because of this guy, which means I would pick high, and this guy I would pick no. That seem reasonable? Same kind of question. I know there are going to be different choices under here, but let's pretend I didn't know the choices. Wouldn't you say no? I would probably say random, but no would probably be what you're going to get. That's pretty strong negative, isn't it? That guy is definitely weak. We might argue about whether it's not, but I think if you look really hard, can you kind of see a downhill thing? But weak and negative. So A should be weak and negative. High, moderate, or no? Whoa. Ooh, I don't know. I don't think I would do moderate. I think they should have gave me weak as a choice here. I would have been much happier. I'm kind of, I guess I'll find out. I'll go moderate, working the assumption that each picture uses one of the three answers. That's the only reason I would have chosen that. I would have definitely said weak if that was me. So far, so good. Right. So let's return and talk. Okay, I've lost yous again. Let's go back now and look a little bit more at what is called correlation is not, I'm screaming that, is not causation. Very often, the reason we do linear regression analysis, why we do what we just did there, is that we're hoping to find a connection between whatever the X values are and the Y. We're hoping to say, look, the height of a plant is one of the main reasons why it weighs so much, which I think is a reasonable assumption in that case, right? And what we're saying when we say that is that there's a strong correlation, right? There's a correlation between the two, and that particular situation is causing it. So I'm about to show you some examples where that is not true. We collect some data on children's shoe size, and vertical, we collect some more data on that same child, and we do their reading age. So if you've ever got a child, if you've had a child, you probably know that there's a thing called its reading age, right? So they go, and sometimes there's standardized tests, and your child gets a reading age, and your child's reading age is 9, right? That basically means they're reading at the level that a typical 9-year-old would read at, right? Now, in some cases, your child is 7, and they've got a reading age of 9, and you should be quite proud of them because, hey, good on you. You're ahead of the curve, right? And sometimes your child is 9 and they've got a reading age of 5. Wouldn't that be an indication that there may be some educational remediation necessary, and catch it quick and things will be fine, right? So this, they do the shoe sizes. So here's the shoe sizes of kids. I have no idea shoe sizes of kids. Anybody want to tell me the kind of size feet that kids get from 5 to 10, right? I just want 5 to 10. What kind of shoe sizes do you get in those age groups? Does anybody know what their 5-year-old brother or sister's shoe size is? Because I have no idea. Okay, none of you do either. So here goes. In this special country, the shoe sizes are 2, 3, 4, 5, and 6, right? So children wear size 3s and size 4s. Oh, by the way, do you know that American shoe sizes are different than European shoe sizes? Well, some of you knew that, right? And up here we had the reading age. And 5, 6, 7, 8, 9-year-olds. And you will discover that if you take a number of children and you find out what their shoe size is, and you also find out what their reading age, you will get a linear correlation like that. And it's a pretty good linear correlation. It's pretty straight, pretty strong, right? To which people make this big mistake. Because this data is nice and straight and linear and quite strong, they are saying shoe size, right, is why people have good reading ages. In other words, the bigger your feet, right, bigger your shoe size, right, bigger your feet, the higher your reading age is. In other words, the size of your feet is the main reason why you read good. Now, you know that's stupid, right? That's not why, you know, you read at a certain age, right? I mean, if that was true, can you imagine some really horrible mothers whose child isn't reading very well? Couldn't you go and get this operation where they break all their bones and stretch their feet out and make them 4 shoe sizes bigger, and suddenly tomorrow they're going to be able to read better? I mean, because that's what it's saying, isn't it? Your big feet, you're going to read better. This does not cause that. Your shoe size isn't the direct cause of what your reading age of your child is. There's a fella called a lurking variable. That's the fancy name they give to it. I like the name. A lurking variable. You know, lurking is like hiding in the shadows. Do you know what the main cause of this table is? It's not your children's shoe size that's causing the reading age. Something more obvious than that. Any suggestions before I tell you? Last chance.
The shoe size is related to their age.
You
As
nailed
they
it.
grow older, they get bigger.
That's it. So what you were really doing was indirectly getting their age, right? Not every child's the same, but would you agree that 9-year-olds or whatever are bigger feet than 5-year-olds, right, in general? And don't 9-year-olds read a lot better, typically, than 5-year-olds? Give you another example of that. So this is what they mean. Just because there is a direct relationship between the two variables, never ever assume that whatever the first variable is causing the second thing to happen, right? Can you see here, shoe size isn't the reason, it's age. Here's another one. If you look at countries in the world, and along the bottom, you record the average number of televisions in a household. And then on the vertical axis, you do what's called the life expectancy, which is on average, how long do people live in that country? You will find this relationship. It'll be linear, at least moderate, if not strong. Correlation, a good straight line fit, that's correlation. Is that the reason that what that's saying is, if that was true, aren't the number of TVs that you have going to make you live longer? You see the problem? That's definitely not true, right? If that was true, wouldn't America not be spending billions sending them over to poorer countries? In fact, shouldn't we not even bother sending them doctors or help medically? Shouldn't we just send them lots of TVs? Right? It's quite stupid. What's the lurking variable here? Which is, what's the real reason that this relationship is happening? What do you think it might be this time? Why do countries with, on average, lots of televisions, why do people in those countries seem to live longer than other countries that hardly have any televisions on average? What are you measuring there when you measure televisions?
How long they're indoors?
Oh, interesting. Keep thinking.
Wealth?
You got it. That's the main reason. If you're in a really rich country, won't you have at least 3 or 4 or 5 TVs in the house? Because every kid wants one, and you've got it for your PlayStation. And I'd probably call monitors. I'm using essentially televisions right now. I'm using 2. Our house is scary. This office has 2 TVs. My wife's working, or when she was working, she's working next door. She's got 2 TVs. We have a TV in the living room and we have a TV downstairs. There's only 2 people in our house and we have 6 televisions. Wealthy countries have lots of TVs, don't they? Most. And the wealthier you are, aren't you likely to have even more TVs? Can you imagine some poor African or Asian countries? You'd be lucky if there's a TV per household. What else is true when you're really poor? Isn't typically when you're in a country where it's, there's not a lot of wealth, don't you typically not get the same kind of medical care? There's not as many doctors, there's not as much medicine, there's not as, the food quality might be worse, all sorts of things, right? So can you see here, the lurking variable here was age, and the lurking variable here was wealth. So whenever a scientist comes up and does analysis, and it comes up and they get a really good linear fit, and they then jump that this is causing that, right? So they're saying this correlation is saying that that's the main reason, right? We have to be very skeptical. Not that it's not true, because many of the times it probably is true, but don't we have to be on the lookout? Is there a lurking variable? Now, it's pretty obvious when it's silly. You can see it. But can you imagine in some circumstances it might not be so obvious, and you are thinking that the first thing is causing the second? I'm trying to think of a medical issue with that. What's the main cause of ulcers? Why do people get ulcers in the stomach? Why do people get ulcers in the stomach?
Is it from stress?
It's from stress. And you know that was known a long time ago that it was stress. But do you know what they found out? That it's not really stress. Does anybody know? I think it's a bacteria in your stomach. Courtney, you're nodding like you've read about it or heard about it. I don't know a lot. Can you remember any more about that thing?
Yeah, I don't know a lot about it either, but I think it's called Helicobacterium pylori, or something like that.
Okay. You know a lot more than me.
But yeah, I remember that it was, and I think it can still be both, but yeah, I think it was new that.
Right. So can you imagine that they may have looked at stress and compared it against ulcers, and they found that there was a correlation. So obviously stress was the main reason for getting ulcers in the stomach, when maybe the main reason was nothing. The main reason, not everything is just one reason, but a combination of reasons. And they discover something else. You know, it wouldn't surprise me if in the future, in fact, now I'm thinking about it. Oh God. Oh, my brain's going. But can't young teenage girls now get an injection or something that stops them getting a particular cancer? My brain is kind of half fuzzled here. Do you know the thing I'm talking about here?
The HPV vaccine?
There you go, thank you. Now, you know, those things come up that people will discover that what we thought was caused just, well, there are lots of reasons you get cancer, right? It's not a one-size-fits-all thing, right? Smoking will give you cancer, right? But you can get cancer because certain chemicals don't agree with your body chemistry, and you can get cancer for all sorts of other things. And so they're continually coming up with cures that weren't obvious because you were looking in the wrong place, right? So who knows, there might be a cure for, oh, there's a new one going out, Lou Gehrig's disease, right? They may come up with a fact that one of the main contributors to that is caused by a faulty gene. And if they can do gene therapy on you, they may be able to counteract that disease. So, kind of drifted a little bit, but we're getting the gist. Correlation is not causation. So if you get a linear thing and somebody says, yeah, the X's are making the Y happens, well, you try and remember TVs and life expectancy, right? It ain't that simple. So let's look at some of those questions now from the homework and see where that takes us. Okay. Over the past few years, there has been a strong positive correlation, right? So positive, straight line going up the way, right? Positive correlation between the annual consumption of diet soda drinks and the number of traffic accidents. So how many sodas people drink and the number of accidents. I think it's pretty obvious in this example that drinking soda is probably not the main reason why traffic accidents have increased, right? And so, no, a strong correlation implies causation. Do you think increasing consumption causes traffic accidents? Well, it's either no, a strong correlation does not imply causation, or no, a strong correlation implies causation. Would you agree it's that one? I'm trying to think of what might cause that. No idea, but here goes. If we are drinking more soda, could that be because that we're richer and we can afford to buy soda? And if you're richer, won't you probably have more cars? And if you have more cars on the road, you're probably going to have more accidents. Now that's pushing the envelope a little bit, but that's all I can come up with. If you can think of another reason for why drinking soda is causing car accidents, then I'm willing to listen. I'm just thinking it's to do with wealth. You get richer, you drink more, you eat more, you do lots of things more, including buying cars, right? If there's twice as many cars on the road, isn't there probably going to be twice as many accidents? I mean, that's just the way things are. Okay. Now, we got this fella here. I hope that you know how to plot points on one of these things, but if I click this one, and I want to do 360, I can go 360, and I can do a dot. Someone told me, I've never done this, that can't you do point and you can just tell it the coordinates and it'll do it for you. So you're just going to learn how to do this. Can I pretend that I know what the heck I'm doing? Can you imagine you plot all the dots and you see a nice straight line? So basically, that's how they get you to draw a scatter plot, right? So I know that's not right, but can you imagine 24, 185, there's 24, there's 185, somewhere round about there would have been that dot, right? Can we pretend, with the exception of that last dot that I've just done there, so I should be able to kill that one. There we go. If that was the correct pattern, would you say the correlation is low, moderate, or strong? Moderate? Okay, You know, if it says wrong, will you just go the other one if you're kind of halfway between two? Okay. There is quite a bit of subjectivity here, isn't there? I don't think there should be subjectivity in the next question, positive or negative. Agree positive in this one? Right. And we are now finally getting there. Do you know that correlation coefficient R that I just said it's magic? And I never gave any indication of where the heck it came from. You know, it's about time we found out how to do it. Right. So you'll need your calculator. And when this video goes online, you'll probably need to pause this until you get used to it. Okay, if you got your calculator, I'll start. This guy is definitely going to be a bit of a pain, but first thing I'm going to do, you only need to do once. So if you do it right now, you can forget about it, it's fixed. For some reason, these TI-84 calculators are not set up in the default value. And the default value is called diagnostics on. So I'm going to show you where it is so we can get that out of the way. You hit the blue button, 0, and you go into catalog, or yellow or whatever color, right? Shift button, 0. So you're looking at catalog, right? And now we're going to scroll through all these. And by the way, this is where every command that the calculator is capable of doing is hidden. So if you can't remember where something is, you could probably do that and find it. Now I'm going to go through this until I get to D, diagnostics on. So hopefully it won't be too far. Oh God, there are a lot of D's. We're getting, hey, we got it. You see I'm now in diagnostics on. You see it? Now you hit enter, and then you hit enter again, and it's done. So if you've done that to your calculator, don't worry about it. It's fixed forever, right? You can just keep doing what you're doing and never worry about it. It's done, right? So you only need to do it once, and it's done. Are we cool? Now, let's suppose I would like to get the correlation coefficient R, and I've got table here, and it's the age, and it's the height of some animal. And it's a baby animal, so 1 month, 2 month, 3 month, 4 month, 5 month, and 12 month. For some reason, I just collected data in those intervals. And the height of the animal was 3 inches, 5 inches, 7, 9, 12, and finally 15. So you can imagine the first year of life of this animal started off as a tiny 3-inch thing, and by the time it's a year old, it's now 15 inches tall. We are going to find the correlation coefficient R. Here it goes. Hit start button. Oh, I'll do that again slowly. Hit the start button and move over to a guy called Calc. Right. We've used tests, haven't we used tests for everything virtually? I think this is the first time, isn't it? No, it's the second time. I think we used Calc. Didn't we use Calc to get standard deviation and mean away back in week 1, week 2? So it's been a long time since we've been to this menu. Now, scroll down. I know number 4 looks right, linear regression, but it's not the one we want. Scroll down. We want number 8, linear regression, because the textbook uses number 8, linear regression, A plus BX. That's just its weird menu. I'm going to hit enter. Okay? And guess, because it's me, guess what I have forgotten to do before I did that? Shouldn't I have put that stuff into my data? Shouldn't I have put that into, guess what, L1 and L2? So here goes. Stats, edit, clear that one out, clear that one out. L1 then, 1, 2, 3, 4, 5, and 12. cross over to the other side, 3 inches, 5 inches, 7 inches, 9 inches, 12 inches, 15. Right. When you look at that, isn't it virtually the same thing as my table, right? It's just turned on its side. Right, now I'll go back and do that poor guy. Hope I'm throwing you too much. Can you remember what number it was hiding under?
8.
There it is. Now, in my calculator, I have to type in L1, L2. Do some of you have the nice modern one that's got a little menu? So do you know your job's a little bit easier because it's probably just hit a lot of enters and you're finished. In my case, blue button 1 gets you L1, comma, blue button 2 gets me L2. So now I can hit enter. There is lots of stuff going on here, but right now the only number I'm interested in is 0.9167. Can you see we now have a way of finding this magic correlation coefficient, 0.917, I've rounded it off. See it? 0.917. You're looking puzzled, Courtney. Are you not getting the same number as me? You're good? Okay. I haven't even bothered to plot that, but I can tell you right now, just using this number, isn't that linear and strong and positive? Linear, strong, and positive. Didn't even bother drawing it. We good? So if you get a question and it asks you to do all that kind of stuff, right? That's kind of how you're going to do it, right? You're going to put it into L1, that'll be your X's, put your Y values into L2, and then go to this menu and, you know, get the good stuff. So, next phase. I know we're not going to make it to, that's fine. When I want to finish this little bit off, and I think there's really only so much any human being can do before, you know, your brain isn't capable of fixing it. So, can you imagine this represents my data, and that blue line represents the best fitting straight line that I could put through that data. Now, if you're thinking about this line there, it's called a funny name in this book. It's called the least squares line. And I have heard that name. Me, personally, I like this name. The best fitting line. I think that name kind of makes more sense, doesn't it? So if you go hunting online, you'll find that this line is called the best fitting line. It's called the least square line. Right. I think it's also called the linear correlation line in some places. So can you imagine this nice fitting line going through that data? Wouldn't it be really cool if we could get the equation of that line? Because the math says that it's unique, right? There's one line that's better fitting through this data set than any other line, right? And if you do an equation of a line, this is the version that the textbook's going to use. So it's going to be something like 5 plus 2x, right? I know it's more algebra, but isn't 2 the slope? Does anybody know what 5 is called from algebra? What's the number 5?
The y-intercept?
Yeah, in this case here, wouldn't 5 be that point there where it crosses the y-axis? So that's called the y-intercept. So I'm going to do a little experiment today where we're going to collect some data and we're going to find the equation of the best fitting line, right? We're going to find the least squares line. And then I'm going to use it to predict and see how good it is at predicting. Because one of the reasons we actually find the equation of this line is so that we can make predictions. So you are only going to take part in this if you feel comfortable. And I am going to put down And you're going to put down the age of your mum and dad, if you're not married and you want to share that, or the age of you and your partner, if you're not. And then the rest of you do not need to share this, and nor should I ask you to. So, I am going to tell you that I am 64, and there's my wife, she's 60. Right. Anybody want to share mum and dad's age or you and your partner's age? I don't care which, it's cool both ways.
23 and 24.
23 and 44? Is that what you said, Chloe? You're breaking up, so you may have said something, but I didn't really catch it.
I think she said 23 and 24.
Oh, okay.
Yes,
Chloe,
thank you.
thank you. It's because, you know, you might not be hearing what I heard. I heard go, yeah, that's kind of what I heard. Which one is the female age, or which one?
Female is 24.
Okay, and the male?
23.
Okay, we good. Right, so tell me the female and then the male one, right? Mum and dad's age, or you can actually tell me your sister's and her husband's age if you want. I just need some data.
Female is 54, male is 64.
Next.
26 and 29, male 29.
Next. 2 more would be nice. I guess if I don't, I can use it. I prefer 2 more.
Female 29, male 28.
And last but not least, we got another one in here.
Male 43, female 40.
Okay, so what we have here is, I'm not going to do the scatter plot part, but what I am going to do is find the correlation coefficient. I'm going to find a guy called R squared, and I'm going to find this equation, and then I'm going to use it to do a prediction. So here goes. Using only this very small data set, we're going to see if we can come up with some useful results. So I'm going to back into stats, I'm going to edit, and I'm going to clear this one out. I'm going to clear this one out. And we'll do the top one. So it's 23, 43, 64, 29, 28, 64. And then I'll move over to the other side. We'll do 24, 40, 54, 26, 29, and finally 60. Right, so pretty quick if you know what you're doing, right? Get the data in. We're going to go stats, we're going over to calc, and we're going to zoom down to number 8, right? In my case, I have to type in blue button 1 to get L1, comma blue button 2 to get L2, and all the data that I want is kind of here. So the R value is 0.9887, and the R squared value is 0.978, and A is 4.6 roughly, and B is 0.81x. But Y and X represent this. So Y is the female age, and it's 4.6 plus nothing 0.81, the male's age. So that is the linear formula written down instead of X's and Y's that don't mean much to people, the male age in the partnership, and this is going to be the female age. Now, would you agree that according to this number, there's not a lot of data points, so that's another reason why it's quite strong, but isn't it strong and positive? This guy here is called the coefficient of determination, although it has other names. And although it's written as a decimal, we actually tend to use it as a percentage. What that is saying is that 97.8% of the variation here is accounted for by the model. It's just a fancy way of saying how good the fit is. Do you know if R squared was 100%, wouldn't it be a perfect fit? And if R squared was 0, it would be no fit at all, right? And R squared is always positive. And actually, it's not just called R squared because they like it. See, if you multiply that by itself, you get this guy. So it is actually R squared. That is very often much more useful, because can't that be negative and positive? And people who aren't into statistics get a little bit, somehow they think negative is bad. Isn't a negative correlation really good? It's just pointing down the way. And they're much more comfortable with a 97.8% fit. You know, if a layman was being told that, wouldn't you say, hey, that's pretty good, right? It's pretty close fit. So prediction time. Someone who has not given me an answer yet. I want you to tell me the male age, but that's all. The male age of the partnership. So maybe it's your granddad. Well, that's if they're alive, you can tell me that one. Maybe it's your sister and her husband or partner. But I need one more for this prediction. Is anybody willing to share one more piece of data?
71.
Right. So the male, your granddad, right, or grandmom, or your mum, or whoever it is, right, granddad, I should say, or father, is 71. Now, according to this formula, won't the predicted female age be 4.6, add 0.81 times the age, 71? So I'm going to go 4.6, add 0.81 times 71, and I am making the prediction here. Ugh, I'm not happy about that, but I'm making the prediction 62. What is the actual age?
She would have been 71 also.
You are a bad choice of data set. But, you know, what this essentially would allow us to do, if I had a big data set, I probably would have gotten a better fit, is that I would have been able to make a prediction based on only one of the two and say, this is what my predicted age for the partner, the female partner in that partnership would be. You can imagine you would probably need a couple of hundred of these to be good at that. But that is basically the formula that tells you what's going on. I think what's happened is that I have some really unusual values. Unusual is not bad. It's just when you've only got 6 numbers, doesn't that one there have a very strong significance? I mean, if there are only 6 numbers, a big difference isn't the going rate 1, 2, 3, or 4, and this one's like 10. So I've got a feeling that that probably caused quite a lot of this discrepancy. Before we finish, and we're kind of getting to that point where I want to, let's tell you some extra, red pen's better. Let's tell you some extra things that you can do in scatter diagrams. Would you agree that that is probably at least linear and positive? We might argue about moderate or strong. Can we just pretend it's strong, right? And right now, it's, because I'm telling you, its correlation is 0.8, right? Let's say I did this and I got 0.8. Sometimes you get a guy down there. It's a data point that doesn't belong in the sausage that most data points lie in. Would you agree linear tends to go up or down, and it's like a big sausage. Everybody's inside the sausage, right? If the sausage is quite fat, won't the R be 0.7, 0.6? And if the sausage is nice and skinny, it's 0.8, 0.9, right? That's one of the things going on. But this guy is not there. This guy has a name that you've heard of. Yes, you're right, Kerry. You want to share it with the rest of us?
It's an outlier.
Now, what do outliers do to your data? They do bad things to your data. This outlier has made a difference to that. That's still pretty good. Do you know if I took that outlier and removed it, this would change. It would probably be 0.9. Can you see what one outlier, even one, and I've got 50 data points, can make? Do you see that guy there? I bet you he'd probably be an outlier if I tried to draw the data. Even although there's 6 dots, can you imagine most of my dots would look like this? And then this one, it would be down here somewhere, right? That's an exaggeration, be over here somewhere, right? So most of my data's here, and then that guy's over there, right? That is what is causing most of the damage. When you try and do a linear model, this thing here, outliers are bad. Outliers distort the relationship. And you are allowed to, and it's not cheating. But if you can identify an outlier, it is allowed for you to kill it and say, I am not going to use that outlier in my table of values. I'm not going to use it in my scatter plot. I'm not going to use it to calculate any of these or that model. Because without that outlier, this analysis is more accurate. Now, one outlier, it ain't a big deal. You are not allowed to say, I don't like half my data because I don't like where it's pointing and I wanted it to point the other way. And therefore, if I call them all outliers, can I make my data point anywhere I like? Or at least can I make my data have a much stronger R value than it really has? So anytime that you remove a data point and you call it an outlier, you must tell people in your report, you know, in the index, wherever you put it, here's all my data. And oh, by the way, here are 2 outliers that I kicked out. This guy and that guy. And what that allows people to do is to look at that's reasonable. Or suppose someone decided that that dot was an outlier. I think they're pushing their luck there, would you agree? And if they said it was an outlier, I would argue that it's not. It just means that the relationship has a bigger, fatter sausage. And so that is a reasonable R value, right? As I say, I was hoping that we would get this done, but at least we've got 9.1 done essentially, right? 9.2 will go pretty quickly because all we're going to do in 9.2 is basically this stuff, you know, get the equation, do a prediction or 2, and probably, if I can remember right, correlation is not causation, you know. Does this prove that? And we're going to say, no, it doesn't prove it. It's maybe true, but it's maybe not. Before you disappear on me,